So I hope you can all see my screen. Okay.
Absolutely.
Okay. So thank you very much for inviting us to talk about our recent publication on covalent reversible inhibitors designed for cysteine proteases. And also welcome to the audience, and thank you for joining this webinar. And also thank you for that kind introduction. So since our work combines quite different topics spanning from computational drug design approaches to in vivo studies, we are today 4 speakers, as Markus already mentioned. So myself, I will give you a short introduction. Bernd Engels will mainly talk about quantum mechanical, molecular mechanical computations, and my co-workers Christian will talk about covalent docking, and my PhD student Natalie, she will present the in vitro and the in vivo studies. So we all hope you will enjoy this talk on quite different topics around one enzyme, and this enzyme is, so I have to look if it works. Okay. And this enzyme called Rhodesain is a major cysteine protease of Trypanosoma brucei, which is the pathogen causing the human African Trypanosomiasis, HAT. So after a short introduction on the parasite and on the enzyme, I will introduce you to covalent enzyme inhibition, especially by Michael acceptor-based compounds. Then Christian will talk about our inhibitor design based on computer-aided drug design methods, namely covalent docking approaches. And after that, Bernd will talk on the quantum mechanical, molecular mechanical, and molecular dynamics-based computations to investigate the inhibition mechanisms on an atomic level. Natalie will then present the mass spectrometry results with covalent and non-covalent compounds, and she will finally present the in vitro and in vivo studies and the anti-trypanosoma activities, cytotoxicity, metabolism, and the biodistribution of our inhibitors. So let us begin with the human African Trypanosomiasis. So this disease is a so-called neglected tropical disease, NTD. The WHO defines such diseases as a group of infections occurring mainly in Africa and affecting people living mostly in rural areas, urban slums, and conflict zones. So several viral diseases, a lot of worm diseases, but also some bacterial and mycobacterial diseases are listed on that list of NTDs, and parasitic diseases, like for example the Chagas disease, which is the American Trypanosomiasis, and leishmaniosis, and last but not least the African sleeping sickness, also called human African Trypanosomiasis. So this disease is caused by 2 different pathogens. The one is Trypanosoma brucei gambiense, causing the disease in the western part of Africa. There is also an East African sleeping sickness, which is caused by Trypanosoma brucei rhodesiense, and there is also an animal disease called Nagana disease, which is responsible for a huge economical burden in these regions. So the Gambiense disease is characterized by a slow development and progression from the first stage of the disease to the second stage. I will come to these 2 disease stages in the next slides, whereas the Rhodesiense disease is fatal only after very few weeks. So people are infected with trypanosomes by the bite of the tsetse fly, which transmits the parasites by blood meals from infected people. The first stage is the so-called hemolymphatic stage, going on with fevers, headaches, itchiness, and joint pains, beginning 1 to 3 weeks after the bite. The incubation period is 1 to 3 weeks for the Rhodesiense disease, and longer by the Gambian disease. The second phase of the disease, the neurological disease, neurological stage begins when the parasite invades the central nervous system by passing through the blood-brain barrier. Progression to this neurological phase occurs after around 60 days in case of Rhodesain, and after around 300 to 500 days in case of the Gambian infection. If untreated, Trypanosoma brucei gambiense almost results in death, with only a very, very few individuals which survive after a long term of around 15 years. And this is, I think, one of the diseases which is, to most people, I think 99% lethal if untreated. So these two stages with the parasite crossing the blood-brain barrier makes it necessary that drugs also have to cross the blood-brain barrier, especially to treat stage 2 of these two infections. So let's now come to the current drugs which are in use. So these drugs are mostly very old drugs, for example, pentamidine or really old drug, which is milazoprol, which is an arsenic drug, which is very toxic. It kills about 5 to 10% of the treated people. We then have the NECT therapy, which means the combination therapy of nifurtimox and eflornithine. And since some years, we have a new drug, which is fexinidazole, which is used for both stages of Gambiense. So for the Rhodesain disease, the stage 2, the central nervous system stage, we only have milazoprol, which is the most toxic of these drugs. So in summary, these drugs are very old. They have high toxicity, severe side effects. Some of them even have lack efficiency, and with the exception of fexinidazole, they are not orally available, but have to be administered via injections. So I think these data show you that there is really a need for the development of new drugs against this disease. So let us now come to our drug target, the enzyme Rhodesain. So Rhodesain is a major cysteine protease of Trypanosoma brucei rhodesiense, but this enzyme is nearly identical to the analog enzyme of Trypanosoma brucei gambiense. So this protease belongs to the papain family of cysteine proteases, and with this it consists of a cysteine-histidine ion pair in the ground state, which means that the catalytically active cysteine residue is deprotonated and the catalytically active histidine residue is protonated. And this is in contrast to, for example, viral cysteine proteases, for example, the SARS coronavirus main protease. So Rhodesain is involved in helping the parasite crossing the blood-brain barrier. It degrades host immunoglobulins. It is involved in the turnover of variant surface glycoproteins of the parasite, and it is involved in the ion acquisition of the parasite. So these properties make it a validated target for drug design. As already mentioned, Rhodesain belongs to the papain family of cysteine proteases, and within this family to the subfamily of cathepsin L-like proteases. So human analogs of this enzyme are, for example, cathepsin L, but there are also other parasitic proteases, namely the falcipains from Plasmodia, brucein from Trypanosoma brucei, which is the pathogen causing the American Trypanosomiasis, the Chagas disease. And there are also Leishmanial cysteine proteases belonging to this family, namely the enzymes CPB and CPA. So as you can see here with the overall structure of all these enzymes, these proteases are highly related. They are highly related in mechanism, in sequence, and in the overall fold. The only exceptions are the falcipains, which have an additional loop. But the active site and the substrate binding pockets are quite similar in all these enzymes. So on the one hand, this may open the possibility for pan-parasitic drugs, maybe, but on the other hand, this may cause problems in selectivity over the related human enzymes, namely the cysteine cathepsins. So after this short introduction to the African sleeping sickness and to the target enzyme Rhodesain, I will come to the principle of covalent enzyme inhibitors with a focus on Michael acceptor-based inhibitors. So some years ago, the term targeted covalent inhibitors came up. And what are these TCIs, targeted covalent inhibitors? These are drugs which are rationally designed to bind and then bond to their target protein. So these inhibitors possess a bond-forming functional group of hopefully low chemical reactivity that, following binding to the target protein, is positioned so that it can react rapidly with a specific nucleophilic residue at the target site and form a bond. When we started to design covalent inhibitors, which is now nearly 25 or even 30 years ago, in I think nearly every talk or every presentation I gave, I was asked why we spend or even lose our time on inhibitors which will never be considered as drugs by the pharmaceutical industry. So covalent drugs were skipped out of every drug design campaign due to several disadvantages I will come to in the next few slides. So since around 10 or 15 years, there's a real hype in covalent drug research, which can also be followed by the publications on covalent drug research in the last 10 or 15 years. So this concept of targeted covalent inhibition was applied in the recent years mainly to kinases. And some examples are shown here. We have, for example, afatinib, we have nazatinib, we have osimertinib, we have dacomitinib, and we have zanoputinib, which most of them bear an acrylamide structure as a reacting so-called warhead. But this approach is also well known from other drugs, like, for example, the DPP-4 inhibitors, like saxagliptin, which are used for diabetes, but also from proteasome inhibitors, for example, bortezomib or carfilzomib, which are used to treat special cancers. And they are well known from hepatitis C virus protease inhibitors, for example, telaprevir. Older examples, you may know, everybody knows aspirin, which is a covalent drug, but also the beta-lactam antibiotics or the proton pump inhibitors are covalent drugs. But in these cases, the covalent inhibition mechanism was not known at the beginning of the development of these drugs, but was discovered only later on. So the most of the new drugs, like the kinase inhibitors, they have an acrylamide moiety or a nitrile moiety as electrophilic warhead. But there are also some other warheads possible, for example, boronic acids for threonine proteases, also for serine proteases, or epoxides, like here in carfilzomib, or the ketoamides in serine protease inhibitors, But there are also some others, for example, an aldehyde structure in the very new drug, voxelotor, or in older drugs, for example, the beta-lactam moiety in the beta-lactamase inhibitors or in the penicillins, or some others, for example, also epoxides, and what is not shown here on this slide, aciridins in anti-cancer drugs. This approach to rationally design covalent drugs has also been followed in the very recent protease inhibitor, namely in this Pfizer compound, which is gone through the journals, through the media, as a very promising therapy to cure COVID infection. This compound contains a nitrile warhead, which also covalent reversibly reacts with a cysteine residue, which is located in the active site of the SARS coronavirus 2 main protease. So why were covalent drugs cancelled from drug design campaigns? Because there are indeed some disadvantages. Due to their reactive groups, the drugs may be unselective. They may react with off-targets, which also contain nucleophilic amino acids, and this may cause toxicity and immunogenicity. So the major concerns against such drugs came, for example, from reactive metabolites of drugs, and the best example is paracetamol. In English, this is acetaminophen, which is liver toxic due to a metabolite, a quinone imine, which results from metabolism and which is toxic to liver cells. So let me also explain the problem of immunogenicity. A non-covalent drug may also bind unspecifically with an off-target. But this compound can easily dissociate from the protein, from the off-target, but also from its real target. And it will also dissociate from the target protein after proteolysis of this target protein. An irreversible drug stays at the off-target and stays at its real target. It inactivates either off-targets or its target itself. Both are irreversibly inactivated, and also after proteolysis of the target protein, some peptide fragments result which bear the drug, and these fragments may induce an immune response. So covalent drugs, on the other hand, have some advantages. The longer residence time can lead to lower dosage needed to treat the patients, and covalent drugs may be less sensitive to pharmacokinetic parameters. These characteristics of covalent drugs have been discussed in the last years in a huge number of review articles. So an approach to minimize these disadvantages and to retain the advantages of covalent drugs is the development of covalent reversible drugs. Due to the covalent reaction, the residence time can be prolonged in contrast to a classical non-covalent drug, but especially after the proteolysis of the target protein, when the binding pocket is destroyed by hydrolysis and the drug can no longer bind pockets, the drug will vary fragments, and this reduces possible immunogenicity. So with covalent reversible drugs, we can combine the possible advantages, and we may not have these disadvantages of covalent irreversible drugs. So how look covalent protease inhibitors like? So they contain a peptide or a peptidomimetic side chain, which is the so-called recognition unit, and which makes the non-covalent interactions between the drug and the target. So additionally, covalent drugs contain an electrophilic warhead, which covalently reacts with the nucleophilic amino acid in the active site of the protease. In case of cysteine proteases of the papain family, the deprotonated cysteine residue. We now have in principle, four different approaches to design a real good covalent drug. We can start from scratch, but this is very, very difficult. So better approaches are to start from a classical non-covalent reversible drug and to attach an appropriate electrophilic warhead. And this approach has mainly been followed with the kinase inhibitors. We can also start from an unselective irreversible inhibitor and optimize the side chains, yielding a selective irreversible inhibitor. So we followed this approach for the design of aziridine-based HIV protease inhibitors. And a fourth approach starts with an unselective irreversible inhibitor and attempts to tune both the reactivity and the affinity to obtain a selective, covalent, but reversible drug. And this approach has been followed in our Rhodesain inhibitor study. So let us now have a look on energetic aspects of covalent enzyme inhibition. There is a commonly accepted two-step mechanism which starts with the formation of the non-covalent enzyme inhibitor complex. So in this complex, the reactive warhead and the nucleophilic amino acids to be targeted, namely the cysteine residue, have to be located near enough so that the next step, the covalent reaction, can proceed. So the question, if this second covalent step is reversible or irreversible, is only depending on the reaction, on the energy difference between the non-covalent intermediate and the final covalently connected complex. So if this energy difference is quite high, then we will have a covalent irreversible inhibitor. And if this energy difference is lower, then we may obtain a covalent reversible inhibitor. So these different steps of covalent inhibition may be treated by several computational methods. The first step by classical non-covalent docking methods, which yield scores which correlate to the stability of the non-covalent complex. Covalent docking, on the other hand, can give us a measurement for the stability of the covalent complex. MD simulations can be used to observe the geometry and to decide about the stability of the intermediate non-covalent complex. And finally, quantum mechanical methods have to be used to exactly describe the covalent inhibition step. And since within a whole enzyme environment, QM methods alone will be too much expensive, there are QM-MM methods used, which means these are hybrid methods, which in detail will be explained by Bernd Engels. There are, of course, other methods which can be used to describe enzyme inhibition, the various steps. However, I mentioned these methods or these approaches since we applied these to our current problem. So in the last years, our group investigated a lot of different electrophilic warheads. And we now have a huge collection of different warheads. Some of them turned out to be only weak inhibitors, some turned out to be reversible inhibitors, and some turned out to be irreversible inhibitors. Our main goal in our research is to get a deep understanding of the reaction mechanisms really on an atomic level, and to get a deep understanding on the reasons why some of these warheads react reversibly, some others irreversibly, and some do not at all react with different nucleophilic amino acids in proteases, but also in other enzymes. And that's why we have this long-lasting collaboration with the group of Bernd Engels, because with his computations, they can give us insights into these questions, and we can answer, or hopefully answer, most of these questions. So let us now start with the development of covalent reversible microacceptor-based drugs against Rhodesain. So our starting point was the compound K1177, which is a very well-known, potent, irreversible vinyl sulfone-based inhibitor. These compounds react with cysteine proteases by covalent attack of the deprotonated cysteine residue at the beta position of the vinyl sulfone moiety, yielding a carb anion, which is then in the next step protonated by the histidinium ion of the active site at the alpha position, and this yields a covalent bond between the enzyme and the inhibitor, which cannot react back to the vinyl sulfone and the enzyme, and which means that the enzyme is covalently, irreversibly inactivated by such compounds. So K11 is a selective compound, selective for cysteine proteases. It does not inhibit serine proteases. It also inhibits related parasite enzymes like the falcipains and brucei. But unfortunately, it is also not selective versus human cathepsins, which makes it problematic in terms of drug development. On the other hand, K11 was found to cure HAT in mice, and it was in preclinical development against Chagas disease and I think also against worm infections. So the main reason why we choose K11 as a starting point is that there exists an X-ray structure of the enzyme inhibitor complex, and this is needed to start with QM-MM computations. So after this introduction to covalent enzyme inhibitors, I will come to the inhibitor design based on computational methods. So we came up with a computer-based design protocol, which starts with the crystal structure of K11 with Rhodesain. And in a first step, we took the warhead, namely the vinyl sulfone. We changed the substitution pattern of this warhead, and the reaction with a low molecular weight thiol or thiolate was computed in solution to predict which warhead might be suitable to be switched into covalent reversible warhead. So these predictions were synthesized, and the reactions were performed in solution to verify the computational predictions. In a second step, we tried to verify these suggestions in the enzyme environment. This was done by the QM-MM computations. Bernd will talk about these later on. So the respective compounds were again synthesized and tested in enzyme assays. In step 3, we attempted to improve the non-covalently interacting parts of the inhibitors by docking methods. Coming to step 4, which uses then QM-MM and MD simulations to check if with these alterations within the recognition unit, the covalent reaction will still take place, followed by synthesis of the predicted compounds and experimental testing. So in our collaboration, we applied these approaches to various problems, mainly in the design of cysteine protease inhibitors, but also in some other cases. So this first cycle, or in the first cycle, we yielded halogenated K11 derivatives shown here, which bear a halogen atom in the alpha position of the vinyl sulfone moiety. So the computations were performed as follows. So starting from the X-ray structure of the covalent enzyme inhibitor complex of K11 with rhodesain, the reaction is computed backwards to the non-covalent complex. And this is a very, very important step because there is no experimental method, or this non-covalent complex of a covalent reacting drug cannot or only hardly be obtained by experimental methods. So in case of the irreversible K11, the reaction energy was found to 23 kcal per mole, which nicely fits to the irreversible nature of this inhibitor. So in a second computation, the warhead was substituted by halogen atoms, and again, the reaction was recorded backwards to the non-covalent complex. So this yielded lower reaction energies for all halogen atoms. For chlorine and bromine, energies were predicted, which should lead to a reversible Michael addition. But in case of the fluorine atom, an irreversible reaction similar to K11 should take place. So additional computations revealed that in case of bromine, a second reaction should take place, namely an irreversible subsequent elimination reaction. So our experiments with the synthesized compounds then verified most of these computational predictions. The compounds are competitive inhibitors. The bromine compound indeed becomes irreversible due to the elimination reaction. The chlorine compound is a reversible inhibitor. We found the highest affinity for the fluorine compound, which is still higher than for the K11 compound. Unfortunately, this compound is not selective versus human enzymes. It's even more active against human cathepsin L. The compound has unfortunately reduced anti-Tryp activity, and it is similar cytotoxic as K11. On the other hand, the affinities we obtained by the enzyme assays correlated quite well with the docking scores we obtained by covalent and non-covalent docking methods. But in contrast to the results which were predicted by the QMMM methods, the experiments showed that the fluorine substituted compound is a reversible inhibitor, which can be reactivated. The enzyme can be reactivated in dilution assays or in dialysis assays. So we have here a discrepancy between the QMMM results, which predict an irreversible inhibition in case of fluorine. In the experiment, we found that the fluorine compound is a reversible inhibitor. And now I will hand over to Christian, who will go on with the next step in our circle, namely improving the inhibitor affinity based on docking studies.
Tanja, thank you so much for the amazing introduction. I will now hand over to Christian.
One second, please. Here we go.
We can see your screen.
Then thank you, Tanja, and very welcome.
Sorry, Christian, if you could switch on your camera, that would be great. So then,
wait a second. Of course, I can do so.
Hey
there.
That's good. No, thanks so much, and sorry for interrupting. Christian, back to you.
No problem. So thanks. Great all to have you here. Hello also from my side. And now let's see how we can improve our K11, which in the first step, we turned from covalently irreversible to reversible by the introduction of the fluorine atom. And by doing so, we just lost some a little bit of potency from 20 nanomolar Ki to 190. And to think this step further, maybe a nice idea might be if we can go from covalent, irreversible, further to reversible. Might it be a good idea to go absolutely non-covalent, just classical non-covalent reversible drug binding? And if we have a look at the binding site, Tanja mentioned just we have a crystal structure of the enzyme inhibitor complex. To make a long story short, this is not a very good idea for the following reasons. In terms of druggability, rhodesain is not in the category undruggable. I don't like this noun, but it's definitely in the hard to drug category. We do not have what we usually want in a nice druggable binding site, a deep hydrophobic pocket with punctual patches for directed interactions. We might see this in the S2 sub-pocket maybe, but if we have a look at the S3 pocket, S1 pocket, or even the prime site of the protease binding pocket, it's kind of open, polar, solvent exposed, maybe some flexible. Though making non-covalent drugs against rhodesain is not impossible, but it's quite challenging. And for the reasons Tanja mentioned, we wanted to have the advantages of a covalent drug while maintaining also the advantages, or not the disadvantage of irreversible, but the advantages of reversible binding. So we wanted to stick at a fluorinated vinyl sulfone at this point. And as you just heard, we lost by making it reversible some of the potency, as you see in the table here on the right. I will just switch on the presenter. Over here, we have lost some potency, and we are not selective, or actually we are selective, but for the human off-target, the human cathepsin L. So that's something we wanted to change as well. And we also lost some anti-trypanosomal activity with 12.5 micromolar, which is also not where we wanted to be. So the goals were pretty clear at this stage. We wanted to improve affinity to gain back to this potency range, definitely improve the selectivity over the human off-targets, cathepsin L and B, improve the activity against the target while staying non-toxic. And from further point, for later on, Tanja explained we need, for the second stage of the infection, our drug to enter the central nervous system to cross the blood-brain barrier, because in the late stage, in the stage 2 of the infection, the parasite enters the central nervous system as well. So we need to get our drugs there as well. And as Tanja mentioned, we wanted to do this by structure-based design. So we thought a little bit about docking and covalent docking, and I think some of you are especially interested in the covalent docking part, so I will explain this over here. There are basically 3 big approaches to deal with covalent docking out there. The first one, also the most common one, is the direct linking approach. In this method, you have the covalent complex predefined. So you have exactly the position where the covalent bond between your inhibitor and your target is formed. So I will show you this in this little video so that you can see it. I hope you can see here over there. The covalent bond is directly formed at the beginning of the docking process. If you cannot see it because it's a little bit too tiny, you have just to trust me. There is always a covalent bond here, and the inhibitor or the ligand is just minimized within the binding site with this constraint that there actually is this covalent bond. It is there, you cannot avoid it, and it actually is not considered in the energetic terms. So we had this nice energy pathway with the non-covalent formation of the complex and the covalent one, and differently what you intuitively would guess, in none of the covalent docking approaches you get any information of the reaction energy. So the way from non-covalent inhibitor target complex to the covalent one. This energetic term is always missing. So we have to be very careful about this. Another strategy for covalent docking, not the direct linking approach, is called steric clash alleviating receptor, in short SCAR method. And this is kind of a workaround because it's actually no real covalent docking. In this method, you do a conventional non-covalent docking, but you use your active site, you mutate your active site residue, your cysteine, for example, to an alanine or even to a glycine. By doing so, you offer more space for the ligand and get your ligand closer to this residue as it would actually get in a conventional docking with the active residue, because you would introduce some severe clashes, which are repulsive interactions and move your ligand far away. By doing so, you get closer to the active site with your compound, but you do not have a covalent step. You just get, theoretically, your nucleophile and your electrophile close together. And it actually works pretty well, even though it's kind of a workaround or cheating around the covalent docking question. And there are also methods in between those two, like the COV-dock algorithm, which starts with this SCAR method. So you mutate your active site residue to an alanine, do a non-covalent docking, but then in the subsequent step, the generated binding poses are filtered to retain only those where your electrophilic atom is close to your active site residue, to your cysteine in this case. And at this stage, after this filter step, the residue is mutated back to the cysteine. The culture is a little bit relaxed, minimized, and then subsequently scored. So it's kind of a two-step approach, starting from the SCAR method and then going to the direct linking 2-in-1. But the only method, if you really want to get the interaction energy of the covalent bond formation, then you have to do these expensive QM methods. There are some ideas out there, but not as the most used ones. There are ideas of using kind of knowledge-based libraries that give you an idea. If the covalent bond is formed, then you have to add this or that number on kcal for the actual reaction. But with these ideas, you have to be careful, because you have to kind of calibrate it to your conventional scoring function if doing so. And another approach, also still not that regularly applied, is the idea of reactive force fields. So classical molecular mechanics or molecular dynamics ideas, where actually the possibility exists for this cutting bond and a bond new formation, but that is still in its infancy, I would say. And what can we now get from our docking strategy? As I mentioned, we used both covalent and non-covalent docking for our prioritization of what to synthesize. So obviously from the non-covalent docking, we get the non-covalent complex. And if we have a quite of solid docking setup, we can be quite confident if how it looks like. For the covalent docking, obviously we get the covalent complex. And now we don't only want the complexes, we wanted, of course, to see which compounds we should prioritize for into this. And there the scoring comes into play. And I think most of you know that's the tricky part of it. For the non-covalent scoring, we get a rough estimate of the delta G of the formation of the non-covalent complex. We all know docking is a highly coarse-grained method, so we should not stress this too much as an absolute number. But if we have a solid setup, which is nicely validated and we can trust in, we can use this score at least to rank within a series of similar compounds what is maybe the better and what is maybe the worse. For the covalent docking, it's kind of a little bit tricky. We just called it stability of the enzyme inhibitor covalent complex. But as I mentioned, you do not get the energy of the reaction, and stability refers more to a sanity check if something weird is going on there. So let's say we compare non-covalent and covalent pose at the first step. We should think of, well, except of the binding or the actual reaction, the actual bond that is formed, there should not happen too much. So of course we have a little jiggling and wiggling here and there, and the pose might differ a little bit, but it should not absolutely turn around, flip around, or doing something strange. And per definition, we have a certain proximity by this additional bond that is formed by the inhibitor and the enzyme. And by this, we might also introduce some severe clashes in other regions between inhibitor and enzyme. And this would be seen in an absolutely high positive score, for instance. So we used the score of the covalent complex more of a sanity check if there's something going on that is weird, that should not happen, which tells us, well, the covalent docking formed this covalent bond, but actually it might not react in reality. So this is our interpretation of the covalent docking scores at this point. And absolutely, what we do not get is the delta G of the reaction. There we need this expensive, computationally expensive QM methods. And of course, we do not get the whole energy profile. And of course, we also do not get the details, the kind of kinetics, how fast do the covalent and non-covalent complex form, or the thermodynamic fingerprints of what's the enthalpy and the temperature-dependent entropy of the complex formation. There are some pretty cool ideas around this for the kinetics with steered MD and so on for at least non-covalent stuff, but maybe we meet in some decades and discuss on this at this time. But nowadays we are far off to get any details on that. Back to our actual target and how we wanted to improve our compounds towards more potency at the first stage, so inhibitory activity on the enzyme. We had 4 positions where we wanted to introduce some variation. We have in green one where the phenyl ring is attached to our vinyl sulfone. We checked for benzyl instead of phenyl or phenoxy, so actually it's a vinyl sulfonate. We have this substituent in the S1 pocket in blue labeled, but it quickly turned out that the homophenylalanine is the best here, so this was not followed up in every detail. The other substituent is the phenylalanine at the S2 position, where we've seen in the crystal structure there is some space and allowed some substitution on the aromatic ring, mainly in the meter and para position. And last but not least, this in black R2 is the substitution which reaches towards the S3 side and which allowed also some derivativization, which was synthetically feasible. And by doing so, we did this by virtual synthesis using our in-house building blocks and those that are easily commercially available. We ended with around about 500 virtual compounds, from which the 33 most promising were actually synthesized. And this prioritization, as I mentioned, was done by covalent and non-covalent docking. On the left panel, figure A, you see the non-covalent. On the right side, you see the covalent binding mode. And we prioritized, yes, sure, based on the docking scores, both covalently and non-covalently. Comparison of both binding poses, though nothing strange happening there, looking quite similar, just a little variation. And especially for the non-covalent docking, we had a closer look at the distance between the catalytic cysteine sulfur ion of cysteine 25 and the electrophilic carbon atom. So you see here 3.0 angstrom, which is kind of an indicator of, yeah, it's pretty close, it might react. And if there are poses where you are 4, 5, 6, 7 angstrom away, you might say, okay, if I trust this binding pose, this stuff would probably not react and not form a covalent complex. And let's now go to our let's say, best of, what turned out to be a good idea. So on the black side, it was a pretty good idea and point to remove this piperazine moiety, remove this basic center, and exchange this by aromatic residues that are less polar and non-basic, non-charged. This had a huge impact on affinity. We improved to 32 nanomolar for covalent-reversible, where the X equals F at this position. And for the irreversible, we ended up with 4 nanomolar, sure, more potent. But what is even more interesting at this substitution is the selectivity. Okay, not just twofold or let's say threefold selective over the cafepsin L, but remember we started off with the 10-fold selectivity for cut L over rhodesain. So this was pretty much one big step forward at this point. We also find this substitution right there quite reasonable with 12 nanomolar, or on the right-hand side next to our electrophilic warhead, the exchange from vinyl sulfone to vinyl sulfonate also turned out to be a good idea. And at this point, we also checked of the double bond, the configuration, if trans or cis is better. So we usually synthesize in trans configuration, but as you see, cis, we checked it for one molecule and said, okay, this is not the way to go. One side to modify left, the red one here, the phenylalanine. The best modifications here turned out to be the methylation, either in meter or even better in para position. So as you see here, it's one of our best compounds, the SJ502. The potency could be improved to an Ki of around about 4 nanomolar, with up to 20-fold selectivity over the human cathepsin L and basically non-inhibition of Cat-B. And again, the vinyl sulfonate was the way to go. So summing up the story here, starting from the irreversible and non-selective K11-777, fluorination turned out to make this compound reversible. We lost some affinity and also selectivity, but both could be regained by modifications of this position, exchanging the basic piperazine to an aromatic pyridine moiety, 32 nanomolar, around about 3-fold selectivity. Further, the methylation of the S2 residue, which improved also both potency and selectivity. And finally, the exchange of the vinyl sulfone to the sulfonate, with ending up with 4 nanomolar potency and this 20-fold selectivity. To make or to close the gap back to the irreversible, we did not want an irreversible inhibitor at the end actually, but if we would want to have an irreversible one, we should get additional affinity by the irreversible reaction, and that's actually the case. This compound SJ502H is the same one as here, just we have introduced the hydrogen again instead of the fluorine, and there we got even potency in the sub-nanomolar range while maintaining some of the selectivity, but of course we also were quite potent against our off-target. And before we now go to how this translates into real in vivo effects on the parasite and on the toxicity, what Natalie will tell you, I would like to hand over to Bernd, who will give you some more details on the QM part and why this fluorine here results in a reversible inhibitor.
To the question again, why the fluorine behaves differently than the hydrogen compound, the K11-777. Tanja already mentioned that we had good agreement for chlorine and bromine, and we also suggested that this is a reversible inhibitor. But the bad thing was that for the best one, we were agreement with the experiment. So we thought perhaps we can learn something what we can do. First, let me go to explain a little bit what are the problems in the calculation you have. You already saw this picture. You have this first step, which you describe by non-covalent. You have this second step where we then do the QMMM. And to put in some more information for the given question, here you see that this is a two-step mechanism now with the enzyme and the inhibitor itself. You see here the inhibitor, and this is of course not in contact with the enzyme. And then you have the first step, which is the formation of the non-covalent complex. You see here that the inhibitor is more or less inside of the enzyme, and of course how it stands in the enzyme is a question of the interaction between the recognition unit and the recognition unit and the enzyme environment for that. Then you have the second step, and the second step is the formation of the bond. You see here you have the thiolate of the cysteine and the double bond and the protonated histidine, and then the thiolate attacks and the histidine transfers its proton. And the question is, does that happen at the same time, or do you have a two-step mechanism? That is an open question, but of course this is a second step. So the first step is the formation of the non-covalent complex, and in the second step we have the chemical reaction. Now, if we look at the first step, you can describe that, for example, the geometrical orientation by docking approaches. Christian already talked about that. You also can make steered MD simulation for that. You also can do it with a force field approach, because you only have non-covalent interaction in that and not a covalent bond formation. You can also get the binding free energies, for example, by scoring functions, or perhaps even better by free energy perturbation approaches using MM, and of course you could also use QMMM, but that is not necessary if you have a good force field. Well, you do not need quantum mechanics. I already said that if you have a good molecular mechanics approach. This is very difficult for itself, and very important to note, this is not part of our QMMM computations. We really concentrate on the second step, and now you see also that we need somewhere a starting point. point. So either we can rely on docking or we can rely on a given X-ray structure. And we thought that it might be better to rely on a given X-ray structure. For this second step, this forming the covalent complex through a chemical reaction, you need for the chemical reaction, you need quantum mechanics. So at least the green part, which we have in here, you have to describe by quantum mechanics, because this bond formation is not possible to describe by force field. Of course, there are a few reactive force field around, but then you have to make a lot of parameterization. Furthermore, but if you do not have this reactive one, then you indeed need QM. So we need QMMM. Why we need QMMM? Well, you cannot neglect the influence of the enzyme. You have actually two important influences. The first one is steric effects. So the inhibitor is more or less oriented in a given way. And the second one is a polarization effect. So you have an enzyme environment, and the enzyme environment influences the inner part of the QM by polarizing it through, for example, some dipole moments or charges or whatever. So you have these two things, and for that you have to include the enzyme environment. The simple neglect of the enzyme is way too inaccurate. So now comes the QMMM in a very small nutshell, where we said that we have an inner part. This is described by quantum mechanics, and you have an outer part, which is described by molecular mechanics. And you see in here that you have important, you have the QM part, which is the Hamilton operator for that. You have the MM part and a Hamilton operator for that. And in a kind of additive scheme, the interaction between the MM part and the QM part, which is very important, you introduce by an additional border Hamilton operator. But if you neglect now that you cut through chemical bonds, perhaps I can show that here, for example, if you cut here or cut there, then you cut through chemical bonds. This is a little bit more complicated, but if you neglect that, then in a way you have the electrostatic interaction between the QM and the MM part and the dispersion effects in that. You can also have a second part. This is a substractive scheme that may be very interesting for you, because this is implemented in the Gaussian program. We also use this part of the Gaussian program, and in that you make it a little bit different. First, you calculate the whole system in the molecular mechanics part, and then you calculate the small system also in the molecular mechanics part. And then you simply subtract those. You see here, you have this MM, the large one, and the small one, and then you add more or less the small one, which you computed by QM. This sounds very simple, but we will see later on this is also quite accurate, actually. So you have the advantage for that. Of course, if you, again, cut through chemical bonds, you have to look a little bit more closely, but I would not like to go detail. What is very important in that respect, and this is even more important than which of these both schemes you use, is a question of embedding. Well, you have here the QM part, which is inside of the MM, so it's in some cases embedded in the MM part. You can make a mechanical embedding, then you neglect polarization effects of the surrounding MM on the QM part. You only take steric effects into account, or on another way to play it in another to explain it in another way. This QM part you make here, you do it simply in a gas phase. And another thing is that you include the polarization of the force field, the polarization of the QM part by the electrostatic environment of the MM part. This is a so-called electrostatic embedding, and for that you also not only take the steric effects into account, but also electrostatic effects. For our example, it's say that you do the QM calculation in a point charge field of this force field. So if you now have a normal force field, so not a polarizable force field, what you include when you use this electrostatic embedding, you include that the MM part polarizes the QM part. Yeah, this is very important because this is various effects. If you use even a polarizable force field, then you can also include that the QM part inside polarizes the MM part in the outer side. Well, you cannot include that if you use a fixed force field, that is clear, but these are the two things. Well, what we use this force field, which only polarizes the QM part. Which coupling scheme is better, the additive one or the substractive one? For a long time, people thought that the additive scheme is much better than the other one. However, a recent paper of Oxenfeld really showed that the accuracy of both is similar. Very important is that you include the electrostatic embedding. This is really mandatory because otherwise you have to use very, very large QM parts. Okay, now let's come back to the problem we had. Well, we were very nice for chlorine and bromine, but for the really good one, we had a problem. And so we thought, okay, perhaps the fluorine do some problems. Perhaps the parameterization of the force field was not good. We only used the B-lib approach to describe the QM part because this was not good, or perhaps the size of the QM part was too small. So we really played around with everything. And then this is a part Tanja already showed. And then we thought, okay, now if you use the improved force field, if you use the improved QM part, then the variation between the fluorine and the hydrogen is much larger. And yeah, well, it was the other way around. They become even more similar. So that couldn't be the reason for that. And then we thought, okay, perhaps something is wrong in our approach to describe the situation. What we need a starting point. I said that we only described the second part of the reaction, so we need a starting point. And we thought using the crystal structure is a good thing, and we get very good agreement for the other systems. So we thought that is nice. So we start here and compute backwards to the non-covalent enzyme inhibitor complex. To get to the halogen, we replaced the hydrogen here by the fluorine, more or less made an MD simulation of the structure again to make a minimization, not only a global a local minimization, but a global minimization, and then we computed back from here to here. Now it could be that by our computation, from starting from the covalent enzyme inhibitor complex to the non-covalent enzyme inhibitor, we missed something. So the question is, how may it happen that we miss something? For that, I give you this model example. You see here the product, and you see your structure here, and you see 4 minima, and you see, and this is especially important, a reaction coordinate, which is important. This is a primary reaction coordinate. But of course, in such a system, you have a lot of other coordinates, and you never compute all the other coordinates. These are the further coordinates, which are called secondary. Now, what you do normally in such a reaction path calculation, you have a given point for the reaction coordinate. So you say, okay, this is a given distance, for example, and then you optimize all the other coordinates and you end up more or less in the minimum. So you always have the minimum in this direction, but you more or less vary now the reaction coordinate. You move a little bit over there. Then, for example, you move over here, and then you make again optimization of all the secondary ones, and then you move to the minima, and so on and so on. And with this, you find the reaction energy path, which goes over here. You see that it is not straight, because if you would straight, you would end up here. But because you always optimize the other coordinates, you really go along a minimum energy path. However, what could happen is that you do not end in the global minimum of the reactant, but you end up in a local minimum of the reactant. And now, if the local minimum of the reactant is not the global minima, it could be that you overestimate the reaction energy. So what you have to do, you first have to look if there are other local minima, for example, by a given MD simulation or whatever. And then if you find another global minimum there, which is lower in energy than the other one, then you could play the game the other way. You start from this one, and then you compute the reaction path using the same method, and you go back. And then you have a given information what happened, because you now start from a different point inside, and yeah, you also may end in another side outside, and so on and so on. But you see that by these calculations, you get an information what really happens. So what we did in that, we said, okay, we take the computed, wait a moment, we take the computed, so we started here, we computed to the non-covalent part, and then we said, okay, we do an MD simulation here to see if we see other lower lying minima. And then we start from that and compute the reaction part from that. Okay, so what we did is we made an MD simulation for the K11777, and we made an MD simulation for the halogen substituted one, and we saw that the hydrogen one really remains where it is. You see here a dihedral angle, which I point out here, and the hydrogen is about, the dihedral angle is about 0. That means the hydrogen points to the left on here within this water side. Now, if you look at the fluorine, and actually, this only happens for the fluorine, not for the other one. That's also the reason why we were in nice agreement with the chlorine and with the bromine, but not with the fluorine. You start, well, you computed it in this direction because you computed backwards. And then you start, and then you suddenly see that the fluorine change. And what changed is that this dihedral angle flips, and then suddenly the fluorine looks to the right. So the hydrogen looks to the left, and the fluorine looks to the right. And then, of course, you are in a different minimum. We also tried that several times, but it always happens. You see that here we made several attempts to see if this is a stable minimum, and indeed it is a stable minimum. And now, what is the reason for this stable minimum? Actually, it is that you have a kind of oxyanion here, which results from the glutamine 19, the serine, and the cysteine, and then the fluorine really wants to interact with them. Here also in the three-dimensional picture, kind of, you see that the fluorine really fits into this oxyanion hole. Actually, oops, wait a moment. Actually, this one and the serine forms the oxyanion hole, and we also have the cysteine included in there. Okay, now what we now do that we use this new one and calculate. Now, the first question is, could that bring a difference in the reaction profile? It could be that you have the same reaction profile before, although you start from another minimum. However, when we looked at it for the orientation for X equal hydrogen, we see that the cysteine attacks from above more or less a little bit. Also, the histidine attacks from above. It's always a syn addition. It's not a trans addition. But if you look at a kind of Burger-Dünitz angle, then this is quite nice, and this is quite nice. This looks quite okay. Now, if you go to the orientation for the fluorine, you see that both the cysteine and the histidine hampers each other to some extent. And also you see that the orientation of the cysteine, the attack of the cysteine, is not as well as it was before. So we had the feeling that perhaps this really changed the reaction path. Okay, now we go to the reaction profile of the K11777. Now we compute from the non-covalent complex to the covalent complex in here. And we see that we proceed through a transition state. This is a kind of transition state. Then it ends up with a kind of plateau. And then more or less you see a strong stabilization of the compound. Overall, you also see that the barrier height is about 12 kcal per mole, and while the reaction energy here is about minus 20 kcal per mole. So it's not the 23, it's a 20, but it's more or less the same. The question now, what happens in there and how did we do the calculation? I said that we have important coordinates and less important coordinates. And in our calculation, the important coordinates is the distance between the proton at the histidine and the carbon, and between the sulfur, the thiolate sulfur, and the other carbon of the double bond. This is a double bond. And then we more or less compute a two-dimensional hypersurface in which we vary the distance, these distance, and always optimize all the other ones. And then from that, we form more or less a one-dimensional reaction profile to show it. And then we see this is the thing we obtained from an MD simulation. We also picked several of these conformations to see if it would strongly change from the orientation in here. And then you see both approach to some extent, but at the transition state, no bond is formed. And then you have a small relaxation in here, which is not too much. And then at 3, you see that first the sulfur bond is formed and the proton is more or less in the middle. And then the strong relaxation, what you see is here that the proton is transferred to this double bond. And then you have the final product, which is now the covalent enzyme inhibitor complex. Now, if we go to the fluorine one, we did more or less the same. However, you obtained a completely different shape of the reaction path. First, you see a much higher reaction barrier, which is now about 27 or even more. And what you see is that you again start from this orientation, which is now the fluorine orientation. Again, you see that both approaches to some extent. And for 3, which is then more or less what you have in between, you see they come even closer. There is not yet a bond formed. The bond is formed if you are on this reaction on the top of the barrier. Then you see again here the bond is formed. The proton, however, stays completely with the histidine at that point. And then after that, you see the stabilization by again transferring the proton to this carbon, to this center, which was then where the fluorine is by this respect. What you see that the reaction barrier is higher. However, what you also see that the reaction energy completely disappeared. You have more or less an endothermic, or the reaction energy is about 0. So this is a point. Now what we have in that one more information, then of course, if you calculate such a reaction path, it could be that you end up somewhere. To make sure that we really found a transition state which has something to do with this reaction, we first determined the reaction barrier, the top of the reaction barrier, and then we made an ESC, so a calculation. So we let start a geometry optimization at that point and look if this geometry optimization really go to the point 1. And on the other side, we started here and really looked if we really end up in the product. And what you see in here is really this ESC calculation. So this is really sure that these points are connected and not somewhere in a potential industry surface. And also, of course, here we did the same. Now we saw that when we react from the fluorine position, then we have a higher barrier. So we thought, okay, perhaps if we rotate the fluorine to the hydrogen position, perhaps the reaction is easier. So what we first made, we started from the F orientation, and then we more or less by stepwise we changed the dihedral angle, and then we moved over this barrier here, and then we ended up in the H orientation. What you see that the hydrogen orientation is about 7 kcal per mole higher in energy than the F orientation. If you would do the same calculation for the hydrogen part, we also did that, you see a difference of about 1 kcal. In that case, for the K1177, the hydrogen orientation is a little bit lower than the fluorine orientation. However, it is only a kcal per mole, so you have more or less a free rotation for the hydrogen, but not for the fluorine. And then we started from here and made the calculation again from here. And you see that this calculation more resembled the hydrogen reaction than the fluorine reaction. You have the barrier, which is again about 27, but this time you start by about 7. So the barrier is only about 20, so lower as before. And you also see that you have a kind of a reaction energy here, because we started from here. You will see in a minute why we started from here by about 7, and you end up by -5, you are something like 12 or something like that. So you see, if you take the fluorine system and let it react from the hydrogen orientation, then the reaction is better than if you would have started from the fluorine orientation. So we thought, okay, we have the following mechanism for the fluorine. First, a rotation takes place from the minimum, from the global minimum for the fluorinated system. You have this rotation around this dihedral angle, and you end up in the hydrogen orientation, and then the reaction takes place, which is again that you first form here at 5. You have formed the carbon-sulfur bond, and then the strong stabilization you obtained again by the hydrogen, by the proton transfer from here. So you go from 1, which is the F orientation, to 3, which is the hydrogen orientation, and then you make the first step, the addition, and the second step, the proton transfer. And that really nicely explained us how everything happens, and also what is the difference between the fluorine and the hydrogen. And this is summarized here, where we found an excellent agreement with the available experimental results. We see that the hydrogen is a irreversible inhibitor. We predict that the fluorine is a covalent reversible inhibitor. This is true thing. You also could have a reversible inhibitor, because the fluorine, if it goes inside the enzyme, it has a strong interaction to this oxyanion hole. So it could be that it stays a non-covalent inhibitor. Well, we describe a covalent inhibitor. However, this is only a small number. And this small number could also be wrong, but nevertheless, we described it as a covalent reversible inhibitor. What is also quite nice, there were measurements for the reaction velocity, and they found it quite astonishing that X equal H reacts 5 times faster than X equal F. Well, we can nicely explain that. It is the case because we have a much higher barrier than, for example, for the hydrogen. However, I said that we said it is a covalent reversible inhibitor, but we were not sure. And with that, I will go to Natalie, which will then show that it is indeed a covalent reversible inhibitor by a given mass spectrometry.
Can you hear me too?
Yes.
Perfect. So thank you. And also a welcome from me to everyone. I will move on to the mass spectrometry and the in vitro and in vivo study part. So why did we do some mass spectrometry? Well, we wanted to confirm the covalency of the bond between our inhibitor and Rhodesain. And we wanted to exclude the possibility that we might only have a very tight binding non-covalent complex and confirm that it's indeed a covalent bond. So we incubated the inhibitor, oh, that was too fast, sorry. We incubated the inhibitor with the enzyme, washed away everything unspecific, and then afterwards we could detect adducts with easy or mild DMS. The first approach was the electrospray ionization mass spectrometry, together with the group of Professor Tanja and from the University Medical Center in Mainz. And we were able to detect protein ligand adducts for our inhibitors with Rhodesain. You can see that down here in yellow, we have the enzyme without any inhibitor as a control. And in blue, you can see the enzyme incubated with the inhibitor. And you can see that we have a mass shift here corresponding to the mass of the inhibitor. Thus, we have an adduct. But there's one problem that we found out. Well, EASY has a softer transition to the gas phase than other mass spectrometrical methods. So this method can also detect non-covalent adducts that are very tight binders. And here you can see an example of such a tight binder. This is compound 42 that was published previously by Klein and co-workers, also a collaboration from our group with the group of Professor Opatz. And you can see in this molecule, we have an electrophilic heterine. Oh, I can maybe turn on my pointer. An electrophilic heterine, which forms a very stable pi complex with Rhodesain that is non-covalent. And here you can also see the ECMS spectra. And you can see that we have in orange Rhodesain without the inhibitor, and in blue Rhodesain and inhibitor. And again, we can see a shift corresponding to the mass of the inhibitor. So therefore, we decided we might try another method to further confirm the covalency of the bond. In this case, okay, it's not going in. Ah, okay. And therefore, we teamed up with Dr. Reda from the Max Planck Institute for Polymer Research in Mainz, doing matrix-assisted laser desorption ionization mass spectrometry. So how does this method differentiate between covalent and non-covalent complexes? Well, it's all about the matrix that you're using, and in our case, we use an acidic matrix, cyanopidic acid, and this matrix can disrupt salt bridges between the non-covalent inhibitor and the enzyme, and therefore suppress the formation of non-covalent adducts. So in the picture, you can see in the top row in yellow in the middle, there we have Rhodesain as a control, and on the top right, you can see again compound 42, the electrophilic heterine, which does not form an adduct in this case. So on the left side, you can see K11777, from which we know it is a covalent inhibitor of Rhodesain. So therefore, in this experiment, it serves as a positive control. And you can see a peak here, which corresponds to the adduct, the covalent adduct that we found. And down here you can see several of our inhibitors that were also incubated with rhodesain and measured. You can see α-fluorovinylsulfones and also sulfonates. And in each case we could see a peak, and therefore we could see an adduct. And that's why we concluded that the fluorovinylsulfones and the sulfonates bind covalently to rhodesain. So that was the mass spectrometry part. And I will move on to the last part of our talk, the in vitro and in vivo studies. So anti-trypanosomal activity, cytotoxicity, and also some ADME parameters that we investigated. So you can see K11777 again, the irreversible inhibitor, and the EC50 value in trypanosomes, which is in the sub-micromolar range, and also the cytotoxicity in HeLa cells, about 10 micromolar. Here you can see 3 of our inhibitors. So on the top right, you see fluorinated K11, and on the bottom, some of our optimized inhibitors, both vinylsulfonates, all reversible inhibitors. And you can see that if we exchange the N-methylpiperazine moiety in the P3 position, that we can decrease the cytotoxicity to 1/100 micromolar. Another interesting thing is that the P3 position, if you put a residue like this DHBD group, we can also increase the potency against trypanosomes to a similar extent than K11 does. So we are also in the sub-micromolar range here, and even though it's just a reversible inhibitor. So we could decrease cytotoxicity and increase the anti-trypanosomal activity of our compounds. We also wanted to look into the some pharmacokinetic properties of our inhibitors, starting out with in vitro metabolism studies. Therefore, we did a microsomal stability assay followed by an LCMS analysis, then synthesized the metabolites that we found in this assay and analyzed those synthesized compounds and compared them to the results from the assay. So we basically just incubated red liver microsomes with the compounds for an hour at 37 degrees, precipitated proteins so that just the compounds stayed in solution and the potential metabolites, centrifuged them, prepared the samples from the supernatant, and then analyzed them via LCMS, also using fragmentation to find out more about the metabolites. Yeah, and we also did control measurements with every compound, just leaving out the microsomes. Here you can see 2 of the compounds that we tested. So on the left side are also the fluorinated K11 again, and on the right side an irreversible vinylsulfonate, the SJ502H. And we can see that we have for JK94 2 metabolites, the N-oxide and the N-demethylated compound, and for SJ502H we only have the N-oxide. We synthesized those and then compared their mass spectra and HPLC traces, and then also tested them in our fluorometric enzyme assay. And we found out that we have similar Ki values for the compounds compared to their parent drugs, so similar inhibitory activity. Then we wanted to look at the biodistribution of our compounds, because as you remember from the talk, as mentioned earlier, for the trypanosomiasis, it's very crucial if you want to treat both stages that you can that you have drugs that can cross the blood-brain barrier and fight the trypanosomes there too. So we teamed up with a group of Professor Klein from the University of Frankfurt, and we did in vivo studies with CD1 mice, and we had 2 groups per compound. The first group received a single intraperitoneal injection of the compound, whereas the second group received per oral applications twice daily for about 5 days. So after the last drug administration, 1 hour later, we took a blood sample. 3 hours later, mice were sacrificed, and another blood sample was taken, and the brain was also removed and homogenized. We homogenized with acetonitrile and water, so we could extract the compounds from the tissue. and all samples were taken back to our lab and then analyzed there via LC-MS. On the right, you can see the compounds we tested. So again, it's the both compounds that we also use in the metabolism studies. And why did we choose them? So first of all, we wanted to have an irreversible versus an irreversible inhibitor. And we also wanted to have inhibitors with different physical-chemical properties. So you can see they differ in the p-values and also the TPSA. And also interesting is that we have here a basic center for JK94, whereas this is not so basic. The results are shown here. So on the left, you see the more hydrophilic JK94. And you can see that we found the compound in plasma samples after 1 and 3 hours, but we did not find it in the brain homogeneisate at all. On the right side, you can see SJ502H. And here, interestingly, you have the compounds in all samples, so plasma and brain samples, and more notably also after per-oral application. So we concluded that it might also be able to be absorbed from the intestines and then also pass the blood-brain barrier. The last thing we wanted to look into is the distribution of SJ502H in the brain tissue. Again, we teamed up with Professor Klein and his co-workers because they are experts for this technique called microdialysis. And this microdialysis can differentiate between extra and intracellular distribution of compounds. So a high dialysate recovery rate also equals a high extracellular distribution of the compound. So in principle, there is a probe implanted into the brain with a semi-permeable membrane. Buffer is flown through the whole time, and then fractions are collected for the dialysate. The results showed that for SJ502H, we only had low recovery rates between 0.8 and 6%. So we figured out that it might have a higher intracellular concentration or distribution in the brain tissue than in the extracellular room. So yeah, that were all our topics for today's talk. And the next slide, I will give a short conclusion of our major findings. So the CADD-based drug design and our enzymatic assays revealed that we were able to improve the warhead and also the recognition unit for our inhibitors to gain covalent reversible slow tight binders with improved potency and also improved selectivity over human cathepsines. QMMM computations resulted in the conclusion that X equals F becomes reversible because it adopts another orientation, and resulting there is a less exothermic reaction profile. Our mass spectrometry experiments revealed that the fluorovinylsulfones and sulfonates bind covalently to rhodesain, and the last in vitro and vivo studies revealed that we have a higher anti-trypanosomal activity, a lower cytotoxicity due to our optimizations. We also have some metabolism going on, and our optimized inhibitors were able to cross the blood-brain barrier and accumulate them in brain tissue, mostly intracellularly. So all in all, we were able to optimize covalent reversible rhodesain inhibitors for selectivity and potency, and we were also able to find compounds with a pharmacokinetic profile that might suit for further development for potential drugs against the human African Trypanosomiasis. So thank you to all collaborators that we're working with, to all our co-workers and also current members of our working groups. And thank you for having us, Biosurvey, and also very much thank you for your kind attention.